So instruction scheduling is one of the compiler optimization passes. And in which part of the compiler is that pass? Yeah.
Code generator?
Yeah, during the code generator. And where is that? Is it in the front end? In the
back end.
Yeah, it's in the back end. So remember, in the earlier lectures, we had the front end, and we had the optimizer, and then we had the back end. And in the back end, we have instruction selection and instruction scheduling, register allocation, and in fact, it's typical for a compiler to have two instruction scheduling passes, one before register allocation and one after. So compilers, many compilers have two instruction scheduling passes, one before register allocation and one after register allocation. So this is what is called the pre-pass or the pre-allocation pass, and this is the post-pass. Why do compilers do two passes of instruction scheduling? Because in the early pass, the pass before register allocation, there is more freedom. Before the register allocator maps virtual registers into physical registers, there is more freedom. Doing register allocation introduces more constraints caused by tying virtual registers to physical registers. We will look into this in detail in not this lecture, but in the next lecture. We'll just look at what it means to have more constraints after register allocation. So the instruction scheduler that runs after register allocation will have less freedom, but there is an advantage. Still, there is an advantage in doing this. Can anyone see an obvious advantage of doing instruction scheduling after register allocation? Yeah.
Probably to reorder instructions to make the code more efficient.
Okay, so that's what instruction scheduling does. Yes?
After the register allocation, the compiler then can see all the conflicts very clearly.
The conflicts between registers?
Between when the register allocation happens, it allocates to physical registers, and it does all of the spilling there. Yeah.
Yes. Okay.
So it can see all of the spills, and it can see what needs to be changed to.
Yeah.
In the first place.
Okay. So these spills are new instructions that the register allocator will add to the code. So before we do register allocation, we have a certain number of instructions. We have n instructions, right? But after register allocation, we will have n plus m instructions, where m is what?
Spills.
Yeah, the number of spills that the register allocator has added. So the instruction scheduler that runs before register allocation does not see these spills. The one that runs after register allocation will see these spills and will try to schedule these properly. Now let's try to remember, from the earlier lectures, what's the main purpose of instruction scheduling? Why do compilers reorder instructions? What's wrong with executing instructions in the original program order, like in this example? Why does, so try refer to the previous, yes?
If there are data dependencies, this will cause a lot of stalls.
Not necessarily data dependencies. Data dependencies cause stalls when? Under what condition? Not all data dependencies cause stalls.
If the following instruction needs a register from a prior instruction, a destination register, for example. So if there's a read following a write, then this will cause a stall, which will cause a delay in the...
And again, it will cause stall if what? Under some condition.
Right.
Say you have a load, in that case, a load X, where it has to access memory. Memory, but the problem is, but as the instruction executes through the pipeline in the CPU, it has to, the pipeline has to stall so that value becomes available.
Okay, so the load is an example of an instruction that has a long latency. So it's about latencies. An instruction that has a long latency, like a load. So this load immediate does not have a long latency. So if the instruction that depends on a load immediate is just loading a constant into a register, loading a constant into a register is not a long latency instruction. It's just loading a number into a register. It's typically something that we expect any processor to do in one cycle. So the instruction that depends on it can execute in the next cycle, and we don't have a problem. But we do have a problem when an instruction has a long latency, like a load, an actual load that goes to memory, that loads something from memory, and loads typically have a latency of a few cycles, like 3 or 4 cycles, depending on the architecture. And of course, this is the latency assuming that the load will hit in the cache. So these latencies are, in fact, the optimistic latencies, assuming that it will hit in the cache. If it misses in the cache, we're talking about hundreds of cycles. If it's, if it has to be brought from main memory. Okay, so it's about long latency instructions. And in this case, let's assume that load latency equals 3 cycles, and the multiply latency equals 4 cycles. So these are the long latency instructions in this example, loads and multiplies. Other instructions, load immediate and add, they have a latency of 1 cycle, so we don't have a problem. Add and or other instructions have a latency of 1. And in our scheduling examples, we will assume a single issue processor, a processor that can issue 1 instruction in each cycle. So we assume a single issue processor. Well, in fact, most processors these days are not single issue processors. Most processors can issue multiple instructions per cycle, but we do a single issue processor only for explaining the concepts of instruction scheduling. And by the way, it's extremely important to keep in mind when we are studying instruction scheduling that a compiler does not actually execute the code. The job of the compiler is to generate the code, to generate the executable. It does not execute it. So when we talk about latencies and single issue and all of that, that's not something that the compiler will need in order to execute instructions. It's only something that the compiler needs in order to simulate what will happen at runtime. So in order for the compiler to reorder instructions properly, reorder them in a way that will optimize performance, it needs to know something about the target processor. It needs to have some kind of machine model. In our examples, our machine model is extremely simplistic. It's an extremely simplistic machine model that assumes a single issue processor, and it assumes these latencies. But in general, in a real compiler generating code for a real processor, machine modeling needs to be more complicated and more accurate than this. So it will have to capture the different functional units on the processor. Latencies, these are static latencies. On a real processor, there are more latencies that are caused by resource constraints within the processor. So within the processor, there are some resource constraints that may cause the actual latencies to be longer than these latencies. So in fact, if you check Intel's programmer manual for the Intel processor, you will see that sometimes they provide a range of latencies. It's not just a single number for an instruction latency. Sometimes they give you a range. So they would say that the latency ranges from 3 to 5, depending on what's inside the machine. So it's modeling is needed for accurate instruction scheduling. But luckily, most modern processors have out-of-order execution, so they take care of most of the scheduling and most of the scheduling of the instructions, and leaving the compiler with only a secondary role if the processor has out-of-order execution. But there is another role that the compiler plays in scheduling, which is minimizing the register pressure, which is something that we talked about in the earlier lectures, and it's something that we will talk about also, but algorithmically in the next lecture. In today's lecture, we will focus on instruction scheduling for minimizing the number of cycles needed for executing a piece of code or a stream of instructions, and for a simple machine model. This is the simple machine model. So now let's do the simulation here based on this very simple machine model to see the number of cycles needed for this instruction stream to execute in its current order. So in its original program order with these latencies, in cycle number 1, we will have instruction A. Instruction A will execute in cycle number 1. Will B execute in cycle number 2? Yeah, because it's not dependent on A. So now we realize that we need to know about dependencies. So B is not. So since we need to know about dependencies, let's draw the data dependence graph. Data dependence graph. The data dependence graph in this case, instructions A and B are independent. And what about C?
It depends on A and B.
Yeah, C depends on A and B. Now, this data dependence graph represents dependencies, but it also captures the latencies. So the latency for A is going to be 1, while the latency for B, which is a load, is going to be 3. Now, what about D and E? Are they dependent on any of the previous instructions?
No.
No, they are not. So D and E are independent. And they feed instruction F. So the results of D and E are consumed by F. And the latency for D is 1. Latency for E is 3. And then C and F feed instruction G. The latency of C, it's an add, so it's 1. The latency of F is a multiply, so its latency is 4. Okay. So now, given this data dependence graph, instruction B, so and again this is simulation. So the compiler now is simulating what will happen. It's trying to estimate the number of cycles that are needed to execute this stream of instructions. We're not actually executing the instructions. C, in which cycle will C execute? So does it have a dependence? Yeah, it depends on B, and there is a latency of 3. So C can execute in cycle 5?
Yeah, it looks like 5.
Yeah, exactly. So it's going to execute in cycle 5 because it's dependent on B. So 2 plus 3 equals 5. So which means that in 3 and 4 we'll have a stall. And in 5 we'll have C. Okay. So now it looks like we are losing some cycles. Now D is independent, so D can go in cycle 6. And E is also independent, so it can go in cycle 7. Now F is dependent on E with a latency of 3. So 7 plus 3 equals 10. So then 8 and 9, the processor will be stalling. And in 10, we will have F. Then G will be in cycle 13. Yeah. So 10 plus 4, oh no, it's 10 plus 4 is 14, in fact. 10 plus 4 is 14, so we'll have 11, 12, 13 are stalls. And 14 is G. So, based on this simple machine model, this stream of instructions will take 14 cycles. But it's obvious here that we can minimize the number of stalls by reordering these instructions. Now, in the overview lectures, we were doing this reordering by inspection. Now, we would like to study an algorithm that will do this systematically. Remember that the compiler is a program, and a program is just a combination of algorithms and data structures that are expressed using some programming language. That's what a program is. So we need an actual algorithm. And an algorithm that many production compilers use for doing instruction scheduling is list scheduling. In fact, list scheduling is not a specific algorithm. It's an approach. It's a general technique, but there can be, what makes it a concrete algorithm is the criteria that are used for selecting an instruction. So it's an approach or a general approach to scheduling. The idea here is to keep track of the ready list. The ready list is the list of instructions that are ready to execute. So initially in this instruction stream, which instructions are initially ready? So these instructions here, because they are independent, they are initially ready. But then as we schedule instructions, more instructions will become ready. So the idea of list scheduling is to keep track of the ready list and to select one instruction from the ready list, to select the instruction that will hopefully minimize the number of cycles. So now in this case, if you were to do this selection, you have A, B, D, and E ready. Which one would you choose?
First one I'd choose would be E,
Why E?
because F takes 4 cycles to complete, so it's E. And when you do that one, then you can execute B, then A and D.
Mm-hmm.
And so while F is executing, you can get C to execute at the same time, and so F will have a lot longer time to execute.
Okay, so your choice of E was based on the fact that the latency of E is 3, so it's a relatively long latency. And also you looked ahead and you looked at the dependent, E's dependent, which is F, and you observed that F also has a long latency. Yeah?
When you choose B first, because you'll use it sooner.
Choosing B first?
Yeah, because you'll use it sooner. You use it as C already.
Mm-hmm.
Yeah. So
Well, but you don't have to do C here, right?
Yeah.
So you are assuming that B will be used sooner, assuming that C will still be in cycle 5, but C may not be in cycle 5. We haven't come up with any ordering yet. So we can put these instructions in any order as long as we honor these dependencies and these latencies. So there are many, many possible orders, in fact. And we are trying to discover the best ordering, the ordering that will minimize the number of cycles needed to execute this instruction stream. So in fact, E is a good choice because the choice of E takes into account the length of the dependence chain below E. And this is in fact a typical approach, a typical priority scheme that compilers implement, looking at the length of the dependence chain below each instruction, or looking at what is called the critical path distance. So the critical path distance for an instruction is the length of the longest path between this instruction and a leaf instruction in the data dependence graph. In this data dependence graph, we have only one leaf instruction, which is G. Okay. So the critical path distance, critical path CP distance of an instruction or of instruction X is the length of the longest path from X to a leaf instruction. And a leaf, we are referring to the data dependence graph. So in fact, in this case, if we label each instruction with its critical path distance, the critical path distance for E is going to be 7. The critical path distance for D is what?
5.
For D, it's 5, yes. Critical path distance for B is 3 plus 1, which is 4. And the critical path distance for A is
2.
So this is the longest path. It's 2. Okay. So we label each instruction with its critical path distance. For instruction C, what's the critical path?
1.
1. And for F, it's 4. Okay, so now let's see with the critical path. If we track okay, so in fact, let's look at here ready list, and the ready list initially has A, B, D, and E. So this is in cycle number 1. We have the ready list has A, B, D, and E, and we will choose instruction. Which instruction?
E.
E. Okay, so we'll choose instruction E because it has the longest critical path. So now we are using the critical path as a priority score or as a priority scheme. So of course, you know, critical path is not the only priority scheme that is used in scheduling, but it's one of the typical priority schemes, and it's a priority scheme that usually gives you very good results in terms of the number of cycles needed to execute an instruction stream. So the idea of list scheduling is to always keep track of a list of ready instructions, and then from the list of ready instructions, the ready list, select one instruction according to a certain priority scheme or priority score, and a typical priority scheme is the critical path distance. Okay, so we select E. Now in cycle number 2, what do we have ready?
A, B, D.
Yeah, A, B, and D. So we select
B.
B or D.
D.
Yeah, so D has a higher score. D has a higher score, so we put
Okay.
D. Okay. Now, okay, in cycle 3, what do we have ready?
A and B.
A and B. How about F? Is it ready in cycle 3?
One more.
Okay, so now we need a way of determining when an instruction becomes ready, right? So now we are in cycle 3 and we are wondering if F is ready yet or not. Well, by inspection, by looking at this example, we could easily answer this question and say, okay, F is not ready because it won't be ready until cycle 4. But we need to do this systematically, in a systematic way. So how would you do this algorithmically? How would you solve this problem? How would you come up with an algorithm or a mechanism for determining what to add to the ready list? Yeah.
And test if D and E have finished, then F is ready.
Well, finished. So how do we know when an instruction has finished?
You could keep track of when the instruction starts to execute, you could have a counter for it. And every time you execute another instruction, you go through and decrement all the counters.
Okay. So there is a counter that keeps track of, for each instruction if an instruction is currently active or executing, we have to count the number of cycles. Right? So for E, we started it in cycle 1. It will become ready in cycle 4, or the results of it will become ready in cycle 4. So in cycles 1, 2, and 3, E is active. So one way of solving this problem is to create another list, which is the active list. And the active list in this case will have E. And here, after scheduling D, we will have E and D are active. Okay. Now in cycle 3, In cycle 3, the instructions that are ready are A and B. Now, instruction F will become ready in in cycle 4 when E is no longer active. So again, we need, thinking of this algorithmically now, we need to track the dependencies of instruction F. So for each instruction, if we can keep track of the number of dependencies. So for example, for C, the dependence count is 2, so it's dependent on 2 instructions. And for F, it's dependent on 2 instructions as well. And G is dependent on 2 instructions, while the dependent count for A, B, D, and E is 0. They're not dependent on any other instructions. So the dependent count here is 0, 0, 0. OK. So we can do this systematically by, for each instruction, checking on each instruction in each cycle if it's active or not. And if it's no longer active, then we decrement the dependence count of all of its dependents. So in instruction 3, for example, in instruction 3, D will not be active. D becomes inactive. So but when D becomes inactive, that will decrement the dependence count of F from 2 to 1, which means that one of the dependents of F, which is D, has completed, and there is yet one more instructions that F is dependent on that is still active. Okay, so here anyway, our ready list is A and B, and we will select B. Now our active list in cycle 3 will not have D in it. It will have E, and it will have B. Okay. Now when we get to cycle 4, now in cycle 4, when we are in cycle 4, E is no longer active, right? And if E is no longer active, then F will become ready. So now F is ready in cycle 4 in addition to A. And how did we know that F is no longer ready? Because in this cycle, the E is no longer active. So now when D became inactive, it decremented the dependence count to 1. When E became inactive, it decremented the dependence count to 0. So when the dependence count of an instruction falls to 0, the instruction becomes ready. So the dependence count of F becomes 0 in cycle 4 when both D and E are inactive or complete. Okay, so now E is not active here. Now what is active is the instruction that we will be selecting. Well, B will continue to be active because it's we scheduled it in cycle 3, so it will be inactive in cycle 6. So B is still active, and our choice here is F or A. Yeah. So F has a bigger critical path. So we will select F. So now F is active. F and B are active now. Okay. Is everyone following this? Mm-hmm. Okay. Now in cycle 5, what do we have active in cycle 5? What do we have ready in cycle 5?
Just A.
Yeah, so A is the only instruction that is ready. Now, if A is the only one that is ready, we have no choice. So we'll just pick A. So A is the instruction that we pick. Now what we have active is B is still active. F, is it still active?
Yeah.
Yeah, F is still active, and A is now active. Okay? Now, in cycle 6, so, well, in cycle 6, which instruction becomes ready?
C.
Yeah, C is the only instruction that becomes ready, because now B is no longer active in cycle 6. B is no longer active. It's 3 plus 3 is 6. So B is not active. F is still active. And is A active in cycle 6? No. A is just a one cycle instruction. So only F is active in cycle 6. But our ready list has only C in it, so we just pick C. It's an easy decision. Okay. Now in cycle 7, what do we have ready?
Nothing.
Nothing. Why? Because F is still active. F will be active for 4 cycles, 4, 5, 6, and 7. And F will become inactive in cycle 8. So in 8, F becomes inactive, and G becomes ready. Okay? Instruction G becomes ready, and we will pick G. So now with this algorithm that is based on the critical path as a priority scheme, now the main point is that this is systematic. So this is not just you trying to come up with the best ordering by inspection. Anyone can come up with the best ordering by inspection for a small example like this with how many? 7 instructions. So this is a piece of cake for anyone. Anyone can can figure out the best schedule for this. But what we are looking for is an algorithm that will work all the time. So by inspection, you can come up with the best algorithm for this. But imagine scheduling 1,000 instructions. So when you schedule 1,000 instructions, you need a something systematic, an algorithm like this. And you need to do some computation like this. OK, so now we got it down to 8 cycles. So any questions on this? Yes?
For number 6, shouldn't C be added to the active list for 1 cycle?
Yes, you are right. Yes. Thank you. Yeah, so here C becomes active, and it's no longer active in cycle 7. Yes, you are right. So in fact, when C becomes inactive, so in cycle 7, when C becomes inactive or it becomes complete, it will decrement the dependence count of G to 1. Then when F becomes inactive, it will decrement this to 0. Yes. OK. Any questions? So now this does not show all the details. So for example, so let's think about these 2, 4, 5, and 7. So we assume that we looked at this by inspection, and we could figure out these critical path distances. Now, can you think of an algorithm for computing these critical path distances? If I give you a 1,000-node graph.
Yeah,
How?
first search.
OK, yes. So DFS can help. Yes, we can definitely use DFS. But when? When should we compute the critical path distance of an instruction, and how in general? When and how? During the DFS. Yes?
When we were constructing the data dependence graph?
No, during construction we cannot. So we assume that, in fact, constructing this will require yet another algorithm. But let's assume that the graph has been constructed, and we are doing a DFS. So what does a DFS will start from? Well, DFS can start from any node, in fact, and whenever you do a DFS, so for each node in a DFS, there is the discover time when you first discover it, and there is the discover time, and there is the finish time. When do you finish a node in a DFS? So for example, here,
A node that has no exits.
yeah, okay. So in this case, you know, if we do a DFS, if we start from A, then the discover time of A is going to be 1. Then we look at the dependents or the neighbors of A. We will find C, and we will discover C at time 2. Then we will look at the dependence of C or the neighbors. We will find G, and we will discover it at time 3. Now G doesn't have any neighbors. Okay, so we will have to backtrack. So now we finish G at time 4, and we backtrack to C. Now C, in general, we will have to look at to see if C has other neighbors. If C has other neighbors, we will have to explore them, and we finish C after exploring everything that is reachable from C. So in this example, C has only one neighbor, but in general, we will have to explore everything that is below a node before we finish it. So now, because there is only one edge out of C, we finish it at time 5. Now when we finish a node, when we finish a node in the DFS, we finish it after exploring everything that is below it, that is reachable from it. So that would be a good time for calculating the critical path distance. How? So let's think of this, you know, in the general and abstract sense. This is a node X, and we have completed exploring everything that is all the neighbors of X, and the neighbors, or let's call them N1, N2, N3 through, or maybe, no, let's do Y so that we can use N for the number. So Y1, Y2, Y3, Y sub N. Now I'm finishing this after exploring everything here. So how can I calculate the critical path of X? Now I'm assuming that I can calculate the critical path of X, and I'm assuming that the critical paths of these are known. So I know the critical path of I1 and the critical path of Y1, Y2, Y3, Yn. Yeah?
Would be the maximum of all of the Ys?
Yeah. Well, the maximum of the critical path of this, but I have to also take into account these latencies. So this is L1, L2, L3, and this is Ln.
Each time you go from X, you go down, and when it comes back up, you add that. You add the latency back to when it goes down, when it comes back up from the recursive call into what?
No, in fact, we cannot calculate the critical path of X until we have calculated the critical paths of all of the instructions that are dependent on X, the immediate dependence of X. So the critical path of X is going to be equal to maximum of critical path of Y sub I plus Li, critical path of Y sub I plus Li, where I equals 1 to n. So going through all of them. So for each one of them, you look at its critical path and the latency. So if we put some numbers here, 5, 2, 3, 1, 4, 3. So in this case, so the critical path is going to be, this is 5 plus 2, this is 7. 3 plus 1 is 4, and 4 plus 3 is 7. So the critical path for x is going to be, in this case, 7. So basically, you have to look at all of its neighbors. And we assume that the critical paths of the neighbors will be available, because all these neighbors will be finished before finishing x. X is not finished until we finish all the neighbors. So in this example, we will first calculate the critical path of g as 0. So the critical path here is 0 for g. Now when we calculate the critical path of c, c has only one neighbor. So it's the max of 1 plus 0. And there is nothing else. So this is going to give us a 1. And when we go to a, it's trivially, again, 1 plus 1, which is 2. Now when we go to then we start another DFS search. If we start DFS from B, now C will have been finished, but we know the critical path of C, which is 1. So then we know that the critical path of B is going to be 1 plus 3, which is 4. Okay. In fact, this is a trivial example, so it doesn't show the calculation of the critical path very well, because we don't have an instruction with multiple children. So each instruction here has a single child. So because we don't have multiple children, so the critical path distance calculation is trivial. So anyway, so this is how we calculate the critical path with a DFS. And what's the running time of DFS?
Log in, I think.
Why log?
No, it's not log in. What is it?
Yeah, so what's the running time? So for DFS, it's V plus E,
Yeah.
where V is the number of vertices and E is the number of edges.